Vector spaces over fields. Recall the following. We have previously looked at three structures called fields. Q, the field of rational numbers, R, the field of real numbers, and C, the field of complex numbers. Each of these fields come with two operations, addition and multiplication. Also, Q is a subfield of R, and R is a subfield of C. This means that every rational number is a real number, every real number is a complex number, and addition and multiplication in Q, R, and C all work the same way. Fields have a particularly nice structure. When working in a field, we can perform all the arithmetic and algebra that we remember from elementary and middle school. In particular, we have closure, associativity, commutativity, identity elements, and inverse properties for both addition and multiplication, with the exception, of course, that 0 has no multiplicative inverse. And also, multiplication is distributive over addition. A vector space over a field F is a set V together with a binary operation plus on V called addition and an operation called scalar multiplication satisfying the following properties. The first property is that V together with addition is a commutative group. Remember that this means, first of all, that we have closure for all VW in V. V plus W is in V. We have associativity for all V, W, and U in V. V plus W plus U is equal to V plus W plus U. We have commutativity for all VW in V. V plus W equals W plus V. We have the identity property. There exists an element 0 in V, such that for all V in V, 0 plus V and V plus 0 are both equal to V. And the inverse property. For each V in V, there is negative V in V, such that when we add V plus negative V or negative V plus V, we get 0. The second property is that we have closure under scalar multiplication. So for all K in F and V in V, K times V is in V. When we take an element K in the field F, we call K a scalar. 3, scalar multiplication identity. If 1 is the multiplicative identity of F and V is in V, then 1 times V is equal to V. We have associativity of scalar multiplication. For all JK in F and V in V, JK times V is equal to J times KV. We have distributivity of one scalar over two vectors. For all K in F and VW in V, K times V plus W is equal to KV plus KW. And finally, we have distributivity of two scalars over one vector. For all JK in F and V in V, J plus K times V is equal to JV plus KV. These 6 properties together are known as the vector space axioms. Let's look at an example. Consider the set C of complex numbers together with the usual definition of addition and define scalar multiplication as follows. For each scalar, K in R, and Z equals A plus BI in C, we define KZ to be KA plus KBI. Very natural definition for scalar multiplication. With these definitions, C is a vector space over R. Let's verify 2 of the properties. We'll verify properties 1 and 4. And of course, you should verify the rest of them on your own to make sure you understand how to do this. Since C, together with addition and multiplication, is a field, as part of the definition of being a field, it follows that C together with addition is a commutative group. So we get property 1 essentially for free. because we already know that the complex numbers with addition and multiplication is a field. Okay, so 1 holds. Let's verify associativity of scalar multiplication. That's property 4. Let jk be in R and z equal a plus bi in C. Then we're going to use the fact that multiplication is associative in R. So we have jk times z is jk times, well, z is a plus bi. So jk times a plus bi, which by definition is jk times a plus jk times bi. That's how we define scalar multiplication. And now we use the associativity in R to rewrite this as j times ka plus j times kbi. And once again, we can use the definition of scalar multiplication to write this as j times ka plus kbi, and that as j times kz. And we've done it. Once again, you should verify the remaining properties. This particular example has a nice geometric interpretation. Recall from the previous lesson, lesson 7, that we could think of the complex number a plus bi as a vector in the complex plane that begins at the origin and terminates at the point AB. For example, in the picture to the right, we can see the vectors I, which is an abbreviation for 0 plus 1i, the vector 1 plus 2i, and 2, which is an abbreviation for 2 plus 0i in the complex plane. We can visualize the sum of two vectors as the vector starting at the origin, that is the diagonal of the parallelogram formed from the original vectors. For example, let's look at the sum 1 plus 2i plus 2 plus 0i, which by the definition of addition, we add 1 and 2, and we add 2 plus 0, and we get 3 plus 2i. Here's a picture of this situation, visualizing the sum as the vector starting at the origin, and that vector being the diagonal of the parallelogram formed from 1 plus 2i and 2. A second way to visualize the sum of two vectors is to translate one of the vectors so that its initial point coincides with the terminal point of the other vector. The sum of the two vectors is then the vector whose initial point coincides with the initial point of the unmoved vector and whose terminal point coincides with the terminal point of the moved vector. So in the picture on the left here, the bottom left, we have 1 plus 2i, and we moved the vector 2 up so that its initial point begins at the terminal point of 1 plus 2i. And then the sum, 3 plus 2i, is the vector whose initial point is at the initial point of 1 plus 2i, which is the unmoved vector, and whose terminal point is at the terminal point of 2, which is the moved vector. Similarly, on the right, bottom right picture, we moved the vector 1 plus 2i over to the right. And this time, the sum 3 plus 2i goes from the initial point of 2 and ends at the terminal point of 1 plus 2i. Technically speaking, the leftmost figure shows the sum 1 plus 2i plus 2, and the rightmost figure shows the sum 2 plus 1 plus 2i. If we superimpose one figure on top of the other, we can see strong evidence that commutativity holds for addition. We can visualize a scalar multiple of a vector as follows. First, if k is a positive real number and z is a complex number, then the vector kz points in the same direction as z and has a length that is k times the length of z. And second, if k is a negative real number and z is a complex number, then the vector kz points in the direction opposite of z and has a length that is the absolute value of k times the length of z. Finally, if k is equal to 0 and z is a complex number, then kz is a point. Let's look at some examples. So starting with a vector z, notice that the vector 2z points in the same direction as z and has twice the length, while the vector 1/2 z also points in the same direction as z but has half the length. The vector negative z, which is an abbreviation for -1 times z, points in a direction opposite of the vector z and has the same length, while the vector -2z also points in a direction opposite of z and has twice the length, and the vector -1/2 z points in the direction opposite of z and has 1/2 the length. Let's look at another example of a vector space. Let R2 be the set of all ordered pairs of real numbers. That is, R2 is the set of pairs A, B, such that A and B are real numbers. Ordered pairs have the property that the pair AB is equal to the pair CD if and only if A equals C and B equals D. For example, the ordered pair 1, 2 is not equal to the ordered pair 2, 1, because even though the two numbers that appear are the same, they're not in the same order. We define addition by the pair AB plus the pair CD is the pair A plus C, comma B plus D. And we define scalar multiplication by K times AB is the pair KA, KB for each K in R. With these definitions, R2 is a vector space over R. Notice that R2 looks just like C. In fact, the pair AB is sometimes used as another notation for A plus BI. Therefore, the verification that R2 is a vector space over R is nearly identical to what we did in the previous example. We can visualize elements of R2 as points or vectors in a plane in exactly the same way that we visualize complex numbers as points or vectors in the complex plane. As another example, R3 is the set of ordered triples A, B, C, such that A, B, and C are real numbers. This is also a vector space over R, where we define addition and scalar multiplication by adding triples A, B, C plus D, E, F to get the triple A plus D, B plus E, C plus F. And K times A, B, C is KA, KB, KC, respectively. We can visualize elements of R3 as points in space in a way similar to visualizing elements of R2 and C as points in a plane. More generally, we can let Rn be the set of A1, A2 through AN such that AI is a real number for each I equals 1 through N. A1 through AN is called an N-tuple. So Rn consists of all N tuples of elements from R. We have the N-tuple A1 through AN equal to the N-tuple B1 through Bn if and only if A sub I equals B sub I for all I equals 1 through N. For example, the 4-tuple 2, 5, root 2, root 2 and the 4-tuple 2, root 2, 5, root 2 are distinct elements from R4. Rn is a vector space over R where we define addition and scalar multiplication by A1 through AM plus B1 through Bn is A1 plus B1, A2 plus B2 through AM plus Bn, and K times A1 through AN is KA1, KA2 through KAN. More generally still, if F is any field, although for our purposes we could think of the field F as either QR or C, we let Fn be the set of n tuples A1 through AN such that A sub I is an F for each I equals 1 through N. Okay, Fn consists of all n tuples of elements from the field F. For example, 3, 2 minus I, root 2 plus root 3I, negative 3I is a 4-tuple of complex numbers, so it's in C4. and 1, a half, a third, a fourth, a fifth, a sixth, a seventh, and eighth is in Q8. Then Fn is a vector space over F, where we define addition and scalar multiplication exactly the same way we did for Rn. A1 through An plus B1 through Bn is A1 plus B1, A2 plus B2 through An plus Bn, and K, A1 through An is Ka1, Ka2 through Kan. Let's look at another example. Let M equal the set of arrays A, B, C, D, such that A, B, C, D, and R be the set of all 2 by 2 matrices of real numbers. We add two matrices using the rule A, B, C, D plus E, F, G, H equals A plus E, B plus F, C plus G, D plus H. And we multiply a matrix by a real number using the rule K times A, B, C, D equals KA, KB, KC, KD. You should check that M is a vector space over R. More generally, we could look at for Mn in Z plus, an M by N matrix over a field F is a rectangular array with M rows and N columns and entries in F. For example, the matrix A equals 5, 2, 1/5, negative 3, root 3, 7 is a 2 by 3 matrix over R because it has 2 rows and 3 columns. We will generally use a capital letter to represent a matrix and the corresponding lowercase letter with double subscripts to represent the entries of the matrix. We use the first subscript for the row and the second subscript for the column. Using the matrix A as an example, we see that A sub 2, 1 is equal to negative 3 because the entry in row 2 and column 1 is negative 3. Similarly, we have A11 equals 5, A12 equals 2, A13 equals 1/5, A22 equals root 3, and A23 equals 7. Let M sub MNF be the set of all M by N matrices over the field F. We add two matrices AB in the set of all M by N matrices over F to get A plus B using the rule little a plus little b sub ij equals A sub ij plus B sub ij. We multiply a matrix A by a scalar K in F using the rule Ka sub ij equals K times A sub ij. For example, let's let A be the matrix 5, 2, 1/5, negative 3, root 3, 7, and B the matrix 2, negative 5, 4/5, negative 1, negative root 3, 1. Then we have A plus B is the matrix 7, negative 3, 1, negative 4, 0, 8. And 2A is the matrix 10, 4, 2/5, negative 6, 2, root 3, 14. Notice that we get the entry in the first row and first column of A plus B as follows. A plus B sub 1, 1 is A sub 1, 1 plus B sub 1, 1, which is 5 plus 2, which is 7. Similarly, we get the other two entries in the first row like this. A plus B sub 1, 2 is A sub 1, 2 plus B sub 1, 2 equals 2 plus negative 5 is negative 3. And A plus B sub 1, 3 equals A sub 1, 3 plus B sub 1, 3 equals 1/5 plus 4/5, which is 5/5 or 1. We get the entries in the first row of 2A as follows. 2A sub 1, 1 equals 2 times A sub 1, 1, which is 2 times 5 or 10. 2A sub 1, 2 is 2 times A sub 1, 2, which is 2 times 2 or 4. And 2A sub 1, 3 is 2 times A sub 1, 3, which is 2 times 1/5 or 2/5. You could check the rest of the entries yourself. Okay, you should also check that the set of all M by N matrices over a field F is a vector space over F. One more example. Let P equal the set of ax squared plus bx plus c, such that a, b, and c are in R, be the set of polynomials of degree at most 2 with real coefficients. We define addition and scalar multiplication with scalars in R on this set of polynomials as follows. Ax squared plus bx plus c plus dx squared plus ex plus f is equal to a plus d times x squared plus b plus e times x plus c plus f. And k times ax squared plus bx plus c is equal to ka times x squared plus kb times x plus kc. For example, if p of x is equal to 2x squared plus 3x minus 5, and q of x is equal to negative 5x plus 4, then p of x and q of x are both in P, and we have p of x plus q of x equal to 2x squared plus 3x minus 5 plus negative 5x plus 4 is equal to 2x squared minus 2x minus 1. And we have 3 times p of x equal to 3 times 2x squared plus 3x minus 5, which is 6x squared plus 9x minus 15. You should check that P is a vector space over R.